Greetings, pre-calculus students, to another lesson in our unit on trig, and now the unit circle. In today's lesson, we will finally establish some kind of relationship, as you can see from the first objective for the day, some kind of relationship between the trig values, the trig ratios, such as sine, cosine, and tangent, and the unit circle itself, the points on the unit circle itself. From there, because don't forget our ultimate goal was to use the unit circle to actually evaluate certain trig values without a calculator. So that's what we're going to end up doing at the end of our lesson, which also encompasses our second objective of the day. So to do that, we're going to be examining three triangles. Much in the same way we did that first triangle in the bell ringer that was a right triangle inside a unit circle, and then we used trig to solve for the missing sides. We're going to do the exact same thing for these three triangles. Now, each of these right triangles have different angle measures, so they're going to have different side measures as a result. And then from there, after solving for the missing sides, we are going to use that information to find the coordinates of the point, much in the same way we did it when we were doing our unit circle and doing the special right triangles. And then hopefully from there we can notice some patterns when it comes, especially when it comes to sine, cosine, and tangent. So let's find the missing sides of each of these triangles first. So we'll start off with this right triangle in front of us, which, as you can see, has an angle measure of 20 degrees in the center. That's the central angle measure. The hypotenuse is 1 because it is the radius going from the center to the edge of the circle. So we are going to determine what these two missing sides are, which we will label A and B respectively. We will label A as the adjacent side because that is the side next to 20 degrees. So that means B must be the opposite side. Once again, we have to use trig to solve for the missing sides of this triangle because this is not a special right triangle. If it was a special right triangle, we can just use those ratios that we've learned about. But since it is not a special right triangle, we have to use trig to do so. So let us solve for the opposite side first. So to solve for the opposite side, since we know the hypotenuse, we're going to use sine, right? Sine is opposite over hypotenuse. So let us do that. Sine of 20 degrees is equal to opposite over hypotenuse, which in this case would be B, because that's our opposite, over 1. Now you'll notice this time, since we have B divided by 1, well, what happens if you divide something, even a variable, by 1? It doesn't change. It just stays B, right? So in this case, our variable is by itself. So at this point, we just have to plug into our calculators, right? We've solved for B. In the past, we would have to multiply both sides by some number to get rid of the number in the denominator. But since the number in the denominator this time is 1, you're just left with that variable all by itself. So B is equal to the sine of 20 degrees. So I'm just going to plug that into my calculator, sine of 20 degrees. And I end up with 0, if we round it to 3 decimal places, 0.342. 0.342. So that is the opposite side of our triangle. All right, now let's solve for the adjacent side really quickly. So the adjacent, we're going to do adjacent and hypotenuse because, once again, we already know the hypotenuse. So for that one, adjacent hypotenuse would mean cosine. And let me do this in a different color. Cosine, all right, gives you adjacent over hypotenuse, which in this case would be A over 1. Once again, we have division by 1. And if you divide something by 1, it does not change. So the variable is solved. Okay, and hopefully you recognize this little convenience in the bell ringer too. Since our hypotenuse is 1, when you divide by 1, nothing changes. So we don't have to get rid of the number since it gets rid of itself. So A is equal to the cosine of 20 degrees, which, if we plug that into our calculators, cosine of 20 degrees, we end up with, rounded to 3 decimal places, 0.940. 0.940. All right, so the adjacent is 0.940. And then the opposite we said was 0.342. Okay, so now recall at this point, the whole purpose we did, the whole reason why we did this is to figure out what the coordinates of point Z, I labeled it as point Z, what the coordinates are for that point. Well, remember, a point has an x value and a y value, and in this case, our x value is going to be the horizontal side of the triangle, because x is horizontal. X is telling you how much to go left and right. So 0.940. Let me give myself a little bit more space here. 0.940 is our x value. And then our y value is going to be that vertical side, because y is how much you go up and down. So that side is literally telling us how much to move up and down. So that means our point is 0.940, comma 0.342. X value, y value. Hopefully that wasn't too bad. So once again, just like the bell ringer, nothing different. Now in this next part, I say to write down the ratios keyword here, for sine, cosine, and tangent. So what I mean is, what did we get? We got 0.940, and then I forgot already, 0.342. So this was hypotenuse, this was opposite. Nope, that was adjacent. This was adjacent, and this was opposite. So what I mean by the ratios, I mean literally the number over another number, the fraction of each of the sine ratios. So sine of 20 degrees is opposite over hypotenuse, which in this case would be 0.342 over 1. And this time we're going to leave it intentionally like that. Okay, we're going to leave it intentionally as 0.342 over 1. And you'll see why once we get later on in the problem. And just a reminder, the point was 0.940, comma 0.342. So that was sine. Cosine of 20 degrees would be adjacent over hypotenuse, which would give us, in this case, 0.940 over 1. And then tangent of 20 degrees is opposite over adjacent, which in this case is 0.342 over 0.940. Okay, just the ratios for each of those triangles. Those will come in handy later on. You'll see. Those will come in handy later on. So that was our first triangle. Okay, that was our first triangle. So for our first triangle, we ended up with a point of 0.940, comma 0.342. Now let's do the second triangle. But in this case, for the second triangle, okay, I'm just going to be figuring out the opposite side. Okay, I'm just going to be figuring out the opposite side. So let's label it as A and B again, because I actually want you to do the adjacent side on your own. Okay, so solve for the adjacent side on your own. So solve for adjacent on your own. Okay, so we're just going to do the opposite side, because for this lesson, I'm going to be focusing on sine as a model, and then you guys can figure out cosine and tangent once you get to that point a little bit later on. All right, so our angle is 30 degrees, so sine of 30 degrees, once again, is opposite over hypotenuse. So in this case, we would get B over 1. Like I said, if you divide something by 1, it just ends up as B, or whatever you ended up with, or whatever you started with. So in this case, B is equal to the sine of 30 degrees. So let me write that out, sine of 30 degrees. So that is 0.5, exactly 0.5. Like, I'm not rounding anything, it's exactly 0.5 if you plug in sine of 30 degrees. So once again, solve for the tangent on your own. And not only that, also solve for the point on your own as well. Okay, so I want you to find the point point y on this unit circle, the coordinates of point y, obviously after you figure out what the adjacent side is. Let's do the ratios again, but once again, I'm just going to be doing the ratios for sine. Okay, I'm just going to be doing the ratios for sine. Whoops, I don't know why I wrote sine. So sine of 30 degrees, since we said the opposite side was exactly 0.5, we just solved it in the previous slide. So that means sine is opposite over a hypotenuse, which in this case is 0.5 over 1. 0.5 over 1. All right. And then cosine, tangent on your own, because like I said, I'm going to be focusing on sine as a model so that you'll be able to do cosine and tangent on your own once you get to that part. Now let's do the third triangle. Once again, I'm just going to be solving for the opposite side. Just going to be solving for the opposite side. So A and B, that's your hypotenuse. That is your adjacent side. That is your opposite side. So sine of 40 degrees is equal to opposite over hypotenuse, which in this case is B over 1. Anything divided by 1 is just itself. So B is equal to the sine of 40 degrees, which in this case is not going to be as nice of a number as 0.5. Rounded to 3 decimal places, 0.643. 0.643 is the opposite side. Once again, solve for the adjacent side on your own. And then find the point on your own as well from there, after you find whatever the adjacent side is. Now let's do the ratios. Once again, I'm just going to be doing the ratio for sine, and you will be doing the ratios for cosine and tangent on your own. Gosh darn it, wrote sine again. Sine of 40 degrees is equal to opposite over hypotenuse. Opposite hypotenuse. So that is equal to 0.643 over 1. 0.643 over 1. All right. Oh, well, there's actually one thing I can add for you guys. There is one thing. Since we solved for the opposite side for each of these triangles, we do know so since this is 0.5, we know the y value of the point. So I'll give you that one. We know the y value of the point because the opposite side, at least in our diagrams, always is the vertical side. And since vertical, right, since vertical represents your y value, that at least gives you the y value of each of your points. So I did do that. You still have to find the x value, though, which you'll find by figuring out what that adjacent side is or that bottom side is. All right. And then this one, 0.643. Okay. So here it is, the conclusion part. So after finding those 3 points, well, you have to figure out the rest of those points on your own and the ratios. Don't forget to do the ratios as well. Okay? So don't forget to do, for each of these triangles, cosine tangent on your own. Okay, on your own. If you don't do the ratios, it's going to be hard to make the conclusion. And you'll see why in a second. Because the first question is, what relationship does the sine ratio have with the actual point? What relationship does the sine ratio have with the actual point? So let's look at the sine ratio for each of the triangles. So for the first triangle, the sine ratio was 0.342 over 1. All right, 0.342 over 1. Let's look at the next one. The next one, for the second triangle, it was 0.5 over 1. All right. For the third one, it was 0.643 over 1. So at the very least, we can say that all of them have a 1 in the denominator, right? I think we're in agreement there. They all have a 1 in the denominator. So let's at least write that down. So sine of the angle, okay, so we'll just call our angle theta. If you remember that variable from before, the angle theta is equal to over 1, okay? That we at least know. All of them had a denominator over 1. Well, now let's try to determine what the numerator was for each of those ratios. So let's look back at it. And what I really want you to focus on here, is the point, the coordinates of the point. So for the first triangle, these were our coordinates, 0.940, comma, 0.342. Well, look at what the numerator was for our ratio. The numerator for our ratio, for sine, remember we're just talking about sine. I'm doing sine with you guys, and then you can do cosine and tangent on your own. The sine ratio was always, it was the y value of this point. Let's look at the next triangle. The numerator, once again, of the sine ratio was the y value of the point. Let's look at the third one. Same thing. The numerator was whatever the y value of the point was. So, and you'll see something similar happening with cosine and tangent as well, once you calculate them and write out the ratios. So once again, whatever the numerator of our ratio was for sine, we're just talking about sine for now, always ended up being the y value of our point. The y value of our point was always the numerator for our sine ratio. So, our conclusion? It's the y value. If you take the sine of an angle, and once again, this is in, the question is specifically in terms of the unit circle. Whenever you take the sine of an angle, you just have to look up that y value of the point. The y value of the point, right? The y value of the point. And once again, you can leave this as y divided by 1, or, since once again, anything divided by 1 is just itself. So sine of theta is equal to whatever the y value of the point that corresponds to that angle, right? Whether it was 30 degrees, 40 degrees, whatever. Whatever point corresponds to that angle, just look up the y value and have your answer. So let me show you what I mean. So once again, you're going to have to do conclusion 2 and 3 on your own. So conclusion 2 and 3 is establishing a relationship for cosine and tangent. But once again, in order to do this, you have to first solve for the adjacent side that I said I wanted you to do on your own for, well, this triangle is already done for you. But I did also write the ratio for you. So solve for the adjacent side for each of these 2 remaining triangles, all right? And then do the ratios as well. Because looking at the ratios, that's when you can see what relationship there exists between the ratios and the point. All right. So let me show you what this actually means. So let's look at this first example. So evaluate each of the following trig values using what you know about the unit circle. Simplify your answers. So this first problem asks us, what is the sine of 30 degrees? What is the sine of 30 degrees? Once again, we're doing this without a calculator. So without a calculator. So we're going to do this just by looking at the unit circle. So sine of 30 degrees. Well, once again, we just said sine of 30 degrees is equal to whatever the y value is that corresponds to that angle measure. Well, let's look at our unit circle, which hopefully you have written down in your notes. I'm going to pull one up right here. So here we go. Here's a unit circle. So if we look at 30 degrees on the unit circle, so if you recall, that was that first point, I think we labeled it point A, right? We labeled it point A on our unit circle, 30 degrees. So that's where the point is. All right. Well, what is the y value at point A? Well, if we look at the y value, right, this is x, this is y. The y value is 1/2. That is our answer. That is our answer. So that means sine of 30 degrees is as simple as 1/2. That is your final answer. Without using a calculator. That is your final answer. And that's it. That's all there is to it, at least for sine. Once again, for cosine and tangent, it's a teeny bit different. Not much harder, but it is a teeny bit different. And then if we do one more, okay, sine of pi over 2, okay, so sine of pi over 2, so once again, we just established that sine is whatever the y value is that corresponds to that point, whatever y value is of the point that corresponds to that angle measure. So let's look up pi over 2 radians on our unit circle. All right, pi over 2. So pi over 2, remember, is, well, whether you remember this off the top of your head or not, pi over 2 ends up being half the circle, so a quarter of a circle. So it ends up being at the top, like the very top edge of your circle. So that is where pi over 2 radians corresponds to. So if we look at the point is 0, 1, but we're looking at just the y value, because that's what we established. We established that the sine would correspond to the y value of the point. And the y value of that point is 1. That means sine of pi over 2 is 1. And you can plug it into a calculator just to be sure, but the sine of pi over 2 radians is 1. So, just to recap, okay, in terms of what I want you to do on your own. I want you to solve for the adjacent sides of the two remaining triangles, so this one and this one. And then from there, I want you to write out the ratios, just like I did with the first one, for those two remaining triangles. And then, from there, hopefully you should be able to establish some kind of conclusion, much in the same way I established a conclusion for sine of theta is equal to, how does it relate to the point? And then from there is one last thing. I want you to do B and C, obviously, because until you establish a relationship for B and C, you can actually evaluate it, much in the same way that I evaluated A and D. All right, so that's what I want you to do. So in addition to the notes that you will be turning in, you will also be submitting your answers for that. Obviously, always feel free to reach out if you're struggling or if you want to make sure that you have the correct conclusion in terms of for cosine and tangent. Otherwise, I hope this lesson went smoothly. I hope that it did. If not, once again, you can always reach out for any questions. Otherwise, I hope you guys stay safe. Enjoy the rest of your days, and I will see you next time.